So today we will continue our class with the DC load line analysis, alright, which actually we have covered a little bit during our previous class, but we will continue a detailed explanation in this slide, alright. So when we said about the DC load line, okay, so what is the DC load line? So DC load line is at the output graph. So when we said about the output graph of your BJT, we are dealing with the output loop analysis, which is your y-axis is your IC current and your x-axis is your VCE voltage. Okay, and we're gonna have a straight line. This straight line is known as your Okay, so this straight line is known as load line. Okay, so to perform this straight line, of course, we need 2 points. This point and this point. So if you read here, a DC load line is a straight line intersecting the vertical axis. So where is your vertical axis? So IC is your vertical axis. Approximately IC saturation, meaning that at this particular point, this is actually your IC saturation, or also known as your maximum value for your collector current, IC maximum value. Okay, meaning that if you keep increasing your base current, okay, your IC will no longer able to increase because it has reached the IC saturation. Okay, so IC saturation also known as IC max. So this is one intersecting point, but then for you to perform a straight line, we need to have another intersecting point. So another intersecting point is at the horizontal axis, which is your VCE equals VCE off. Okay, so this is our next intersecting point at the horizontal, which is known as your VCE off. Okay, this VCE off, alright, happen during what will happen to your IC? Our IC on this particular point is equals to 0. For your IC saturation and IC maximum, this occur when your VCE, what will happen to your VCE? Our VCE is equals to 0. So you can look at this graph. When your IC is maximum, what will happen to your IC? What will happen to your VCE? Your VCE is equals to 0. But when your VCE off, okay, what will happen to your IC? Our IC is equals to 0. And if you look at this particular equation, okay, how this equation is coming out? This equation, since that this is at the output graph, we are dealing with this KVL at the output loop. KVL at the output loop said that we have learned and we have discussed this negative VCC. Okay, so this KVL at this particular loop, yeah, plus ICRC, plus VCE is equals to 0. Okay, I think I did show to you, okay, how to draw this. Okay, sometimes it's very difficult, kan, for you to look the loop at this particular part. So this is your VCC, and this will connect to your ground. Okay, so your emitter is going to ground. This is your VCE, this is your IC, this is your VCC, and this is our RC. Okay, so if we perform the KVL here, it will become negative VCC plus ICRC plus VCE. Or if you look at this loop as well, or if you look at this circuit as well, positive VCC is equals to ICRC plus with the VCE. So either way, you will get the same equation. So since that this is our output graph, this equation is important to us. Okay, so now based on this equation, to get this intersect, to get the first intersecting at the vertical axis, our VCE is equals to 0. They mentioned our VCE must be equals to 0. So therefore, this VCE is equals to 0. So what will happen? Your equation will be IC RC is equals to VCC. Okay, so our objective is we want to get this value of IC. So therefore, IC equals to VCC over RC. So see, you will get the same equation. Alright, but this is only true if your VCE is equals to 0. So you will get this 1 point. Alright, so the IC that you have calculated here is the IC saturation. Okay, so that's why it is written as IC saturation. Next, how to get for this particular point? So for this particular point, we know our IC is equals to 0. So back to this equation, let's use different color. I'm using my purple color. Okay, so for this intersect, our IC is equals to 0. So now this IC is equals to 0. So when IC is equals to 0, what will happen for this whole value? It will become 0. So therefore, your equation will become VCE is equals to VCC. Okay, when your VCE is equals to VCC, so we said on this particular area, okay, our VCE is off. Okay, because of why? Because the value of the VCE here will be same as the value of the VCC, meaning that your VCE will not affect anything lah. It will take straight away the value of VCC. It is not work at all. Okay, it will not have a voltage drop or any voltage difference. So it is exactly as the amount of your VCC, and during that particular time we said our VCE is equals to off. Okay, and this is only true if your IC is equals to 0. So therefore you're gonna have two lines, then you can make a straight line. So this is for how for you to perform or how you want to get this DC load line. Okay, alright, clear, yeah? Okay, so this is it. Okay, alright. Okay, so this is same repeating. So one is when your VCE is equals to 0, then we will get the value of IC. Another one, when your IC is equals to 0, then we will get the value of VCE equals to VCC. Alright. Okay, so Q point, the Q point must be lies on this DC load line. So Q point cannot be somewhere else. It must be on this DC load line. Either it is here, here, here. Okay, it must be along the DC load line. Alright. So once you're gonna have your DC load line, then only you can determine where is your Q point. Okay, so you can see your Q point has a possibility to have a different location. It can change. Kenapa? Why it can change? Because it depends on the value of VCC over RC, which is depends to the RC value. It also can depends on the VCC value, alright, and it also can depend, yeah, it can depend based on these two values. Okay, so now let's look what will happen if you change. Oh yeah, it also can depend on the value of IB. Okay, it also can depend on the value of IB. Let's say if you increase the IB or you decrease the IB, of course this point will be different. Okay, so now let's look how the Q point position can be changed if we change the value of IB, RC, and VCC. Okay, so when our IB is changing, let's say you change the value of IB. We need to relate back with the equation that we have learned before. Beta IB is equals to IC. So what will happen? What will affect when your IB is changed? Your IC will be changing as well. So IB will affect the value of collective current. So your IC will change. So therefore, your position of y-axis will be changed. So you can see here, IB is changed. So you mean that when you increase the value of IB to a higher point, your Q point will be increased to a higher position of your DC load line. But if you decrease the value of IB, the Q point will move to the bottom DC load line. Increase the value of IB, your Q point will move to the higher position of your DC load line. So that is the changing or the affecting of your IB current. Okay, will this position change? No, this position, your DC load line, the DC load line here, this DC load line will remain the same. The only change is the position of your Q point itself. Okay, only the Q point is changing if you change the value of IB current. Okay, next, okay, what will happen? Okay, what will happen if you change the value of resistor? So R1, R2 and R3, this is the value of RC, resistor RC. So where is the resistor RC? I draw it again so that you can remember. So this is going to this one. So this is your resistor RC. This is the resistor RC, this is the VCC. So now this value of resistor is changing to R3, R2 and R1, which is R3 is larger than R2, then R1. So what will happen when you divide this value to a larger value? Any numbers, VCC is maintained. Any numbers divide with a higher value or larger value, of course, you will get a smaller value, right? This is going to be the smallest. This is smaller. And this is the small value lah. Okay, so the value will keep decreasing. So it means that this position will be changing. Your DC load line now will be changing because one of the intersecting point is changed. Okay, however, this intersecting point, will it be changed? No, because your VCC is same value. Okay, so only this point is changing. Alright, so when this point is changing, what will happen to your Q point now? So of course, your Q point will change as well. So it's gonna change to the left or to the right. So meaning that if you decrease the value of R1, it will change to your right. But if you increase the value of RC, it will change to your left. Okay? Okay, so when you change of RC, when RC change, okay, Q point also will change. Alright, differ with the IB. When IB change, Q point change, but your DC load line will maintain. Okay, but when your RC change, of course your Q point change and your DC load line will change as well. It change in terms of what? The intersecting. Okay, intersecting vertical will change. Okay, intersecting vertical axis change. Okay, will change. Alright. So it will change of your Q point. Okay, next, what will happen when your VCC is now changing? Okay, our VCC now is changing. So when your VCC now is changing, what will happen? Of course, the intersecting of the vertical line is changed, and the intersecting of the horizontal line also will change. So when your VCC is changing, intersecting horizontal and vertical will change, and due to that, what will happen? Of course, our Q point also will change. All right. Okay, so this you're gonna have a new DC load line. However, all these three DC load line, first, second, and third, all these three DC load line will have a similarities. What are the similarity? It will have a same gradient. Kecerunan dia sama. You're gonna have a same gradient because the VCC here is same and the RC here is constant. So meaning that the first DC load line and the second DC load line, you are gonna have same gradient. Same goes to for your third DC load line. Alright. Okay. So this is the effect when your when IB, RC and your VCC is changing. Okay. So now let's look at example number 12. Okay. We need to have, or we need to know, or we need to form the DC load line. Okay, it's given to us the graph here, IC and VCE. So first of all, we need to perform the DC load line. Okay, how to get this DC load line? Alright. Okay, we need to draw the DC load line. So how to draw the DC load line? Of course, we need to use the KVL at output loop, right? So KVL at the output loop will give us, but by right, I think you should memorize already, yeah? Equals to 0. Okay, so at this particular point, to get this particular point, it will be our VCE is equals to, at y-intercept, our VCE is equals to 0. So therefore, IC, RC is equals to VCC, and IC is equals to VCC over RC. And what is the value of VCC? 8 volts. What is the value of RC? 2 kilo. So of course, we will get 4 milliampere. So this is your y-intercept. Okay, so 4 milliampere. Next, at x-intercept, based on this equation, what will become 0? Our IC is equals to 0. So therefore, we will get our VCE is equals to VCC. And what is the value of the VCC? VCC is 8 volts. So here is your 8 volts. Then we can draw a straight line. So this will going to become your DC load line. Okay. Next, so in this graph, they didn't provide to us the base current. Okay, the base current. So what we need to do, we need to find the value of IC. We need to find the value of VCE. Alright, so the value of IC, okay, during this operation, we need to perform the KVL as well lah. The KVL at input loop. Okay, so KVL at input loop, it's gonna be okay, it will be KVL at the input loop. We're gonna have RB VCC, negative VCC, plus IB RB. Okay, IB RB plus how much? IB RB plus with the VCE equals to 0. Okay. Okay, and From here, we will get our IB to become VCC 8 volts minus, this is BE, 0.7 divided with RB 360 kilo. So we will get the value of IB. However, beta is not provided to us. The value of beta is not provided to us, meaning that we cannot find the value of IC based using this calculation. So in this case, what we can do is, to know what is the best operating point of this IC, we need to determine. So how to find that? We need to find the center from this DC load line. So this is the DC load line that we have calculated just now. We need to find the center. So from 4, 0 until 4, okay, we can just assume, okay, from 0 until 4, the center will become 2 milliampere. So it is 2 milliampere. From 0 until 8, the center will become 4 milliampere. 4 volts. Okay, center 0 until 8, meaning that 8 minus 0 divided with 2, so you will get 4 volts. From here to get the center is 4 milli minus 0 divided with 2, so you will get 2 milli. So we will draw the straight load line, okay, from 4. Okay, so this will become our Q point. Okay, so that is the determine of the Q point. Alright. Okay, so this is the calculation. Alright. So now let's go to the example 13. So example 13, given the load line in the figure, define the Q point. Okay, so they have given the load line. So this is the load line. Determine the required values of VCC, RC and RB. So if we can look here, we have VCC, RC and RB. So how is the graph? How is the circuit? The circuit, we're gonna have, this is our RB. RB usually goes to the base, kan? Goes to the base. And then at emitter side, we don't have any resistor. So therefore, emitter will go to ground directly. And then we're gonna have RC. So this is our RC. This is our RC. And then it has VCC here. Okay, VCC. So the what we have to determine, okay, the value that we need to determine is the value of RB, the value of RC, and the value of VCC. And they give to us, assume the value of IB is 17. So, and they provide, the graph provide to us the location of Q point. Okay, Q point is given to us. This is the location of Q point. However, what is the value of IB? They mentioned the value of IB during this particular point is 17 milliampere. Okay, so they provide to you. So let's say, okay, I would like to mention to you, if during test or during final, the value of IB is not provided, you can make an assumption. Maksudnya, it means that the value of your IB, it can be between 20 micro to 10 micro. So you can take around 15 micro, 16 micro, 17 micro, 18 micro, 19 micro, it will not be wrong. Okay, but if the value is given, the assumption value is given, then you have to use the assumption value. Alright, but if it is not given, then you have to use, or you have to take the value of IB between the range of 10 microampere to 20 microampere. Clear, yeah? Alright, so now we want to calculate what is the value of the RB, RC and VCC. Okay, so in this case, okay, so now let's look here. Alright, so this is the circuit. Alright, so we know what is the KVL. Based on this load line, we know the KVL at output loop, right? KVL at the output loop, it mentioned to us what? Negative VCC plus IC RC plus VCE equals to 0. And this intersection mentioned to us is when our VCE is equals to 0, y-intercept, VCE is equals to 0, the equation will gonna be IC is equals to VCC over RC. Okay, do we know what is this value? It is actually 15 milliampere, right? So meaning that 15 milli VCC over RC. Okay, so this is our first equation. How about our x-intercept? X-intercept will give to us when our IC is equals to 0. So based from the equation, the VCE is equals to VCC. So meaning that what is the value here? 40 volts. So VCE is equals to VCC equals to what? 40 volts. So from here, we know what is the value of VCC already. So VCC is equals to 40 volts. So here will become 40 volts. Okay, 40 volts. So can we find the value of RC? I couldn't write there. No. Okay, so from here, can we find the value of RC? Yeah, right? So 40 volts divided with 50 milli. So we will get the value of RC is equals to 2.67 kilo ohm. Alright, 2.67 kilo ohm. So we know the value of RC, 2.67 kilo ohm. Okay, next, can we determine the value of RB now? Yes, right? We can use the KVL at input loop. Okay, so KVL at the input loop will give to us negative. Here is also VCC, right? VCC, negative VCC plus IB, RB plus VBE equals to 0. They mention the value of IB is 17 micro. So meaning that negative 40 plus 17 micro RB, VBE always 0.7. So from here we can find the value of RB, right? So the value of RB will become 2.311 mega ohm. Okay, 2.311 mega ohm. Alright, so from here you will get the answer to be as such. Okay, so this is the answer, 2.311 mega ohm. The answer there is wrong a little bit. Okay, so let's check, is it correct? 40 minus 0.7 divided by 17 micro, 10 to the power of micro, yeah, negative 6. Yeah, we're gonna have my mega. So the answer provided here is not correct. This is the correct answer, 2.311 mega ohm. Okay, so this is how we want to solve if it is provided to us the Q point, and then the value of IB, and they ask us to find the value of RB, RC, and VCC. You have to do the KVL at output loop first, then only you do the KVL at input loop. So it is an opposite with the mathematical analysis lah. Mathematical analysis, you need to start from the KVL of input loop, and then only the KVL at output loop, right? Okay, so this is the other way around. Okay, so now let's look at another example. Okay, so this is the calculation. Okay, so this question is same. Now let's look at another example. Example number 14. They ask about the determine the saturation current and the cut-off voltage of the circuit. The cut-off voltage of the circuit. So in this case, they want to know what is the value of the saturation current. So it means that IC saturation. So IC saturation is what? What is the equation of the IC saturation? Remember, negative VCC plus IC RC plus VCE equals to 0, right? And to find the IC saturation is when your VCE is equals to 0, right? When our VCE is equals to 0. So when your VCE is equals to 0, you will get IC saturation. So from here we can get IC saturation is equals to VCC divided with the RC. So what is the value of VCC? This is our VCC, 20 volts. What is the value of RC? This is the value of RC, 2 kilo. So we will get the value of IC saturation is okay. Now in these questions, yes, in these questions we have RE. Okay, so we know, yeah, when we want to solve this, we need to remove our capacitor. Okay, we need to remove our capacitor. So the equation, instead of this equation, our equation, because we have the RE now, this is without RE. Now we need to consider RE. So slightly different here. Slightly different here. Okay, we need to include the RE. Okay, we need to include the RE. So it's gonna be negative VCC plus IC RC plus VCE plus IC RE, right? Because this is IE. We know for a good amplifier, IE is almost to IC. Okay, so it is equals to 0. So I just take that, alright? So from here, negative VCC plus IC RC plus RE plus VCE equals to 0. So IC is equals to, for IC saturation, we know for IC saturation, VCE is equals to 0. So it's gonna be VCC divided with RC plus RE, because our VCE is equals to 0, right? So we're gonna have 20 volts. RC is equals to 2 kilo, 1 kilo. So you will gonna have how much? 20 divided with 3 kilo. So you will gonna have 6.67 milliampere. Alright, so for the cut-off voltage of the circuit, so cut-off voltage of the circuit, this is when your VCE is equals to VCE off. Okay, so we know for the VCE off is our IC is equals to 0, right? So we're gonna use this equation again. Okay, so IC is equals to 0, negative VCC plus IC RC plus RE plus VCE equals to 0. So here is 0. So of course all of this will become 0. So your VCE off is equals to VCC, right? VCC, which is equals to 20 volts. So these are the answers. Okay, same as what the answers shown here. All right. Okay, so I think we have covered, okay, the DC analysis, load line analysis. So our next lecture we will cover it for the AC analysis. So thank you everyone. So meet you on the next lecture.